Okay, so the first keynote of the session 3, because of coordination problems, won't be ensured by Federico Edani, but by myself. So I have tried to prepare something which talk about the implement control and the synchronization between control and mobile platform in order to achieve more accurate task. And I will try to do my best. I think I will come with more questions than results. So nowadays we have talked a lot in this FIRA, International Forum of Robotic Agriculture, of the benefit of the robotics to face some problems with respect to the evolution of the agriculture, with respect to the environmental impact, with respect to the preservation of the level of production, the risk exposure of farmers, and the fact that we have a lot of penalty in achieving agricultural works, and we have shown that robotics can help in having new principles for agriculture, such as precision agriculture, agroecology, or biological agriculture. Since each of these solutions requires to have more and more manpower and more accuracy. But robots are here to help humans in working in agriculture, but it also can be used to find new concepts for agriculture. So instead of having big machines, we can have small robots who have the time to do a very precise job and to act at the plant level. Unfortunately, if we have some connection with the field of autonomous vehicles, we have some differences because autonomous vehicles are moving into known environments. We have some structure. We have some prerequisites. We have some knowledge about the potentiality of parameters, of interactions. And also the only task in transportation systems is to move from one point to another, even if we transport goods or if we transport people. But in agriculture fields, the idea is that we are making something on the earth and we are making something on the vegetables. And then we have to develop implement. And what is important in agriculture is the interactions with the vegetations and with the earth. And so nowadays, what is done in such fields of application is first we have activated implement, which are mounted, activated tools which are mounted on manually controlled machines, such as Garford, such as some proposal about John Deere. So in both cases, we have a conventional tractor, which are moving thanks to the farmers or the operator, and the implement adapt with respect to what the farmer is doing. The second way is we have robots, but we have passive implements. So robots can move autonomously, and it tries to position it the best with respect to the vegetation, but the implement, the tool, is passive, so just you transport it. We have also both active implements and active mobile platform, autonomous mobile platform. It's the case for eco-robotics, which is a moving robots, and while it is moving, the implement is doing things, because for eco-robotics we have manipulator arms, so parallel manipulator arm, not with cables, such as we have seen in previous session. Or the case of Pumagri, who in this project we have moving robots. Moving robots, moving platforms. Nowadays it's called Tractor. So you can see it. It's manufactured now by CTI, and this is a prototype in the project Pumagri. And we have also an active implement. Once again, sorry. Hop. But in both cases, the motion of the robot is not linked to the motion of the implement. There is no connections, no synchronizations between the fact that the robots move and the fact that the implement moves. So no synchronizations. Last point of view is that you have a mobile platform who can move and detect something interesting and just stop. And then you have implements who are doing things, such as Wageningen University or Octinion projects, where we go through, the robot moves from 1 meter to 1 meter, it stopped, and independently, the robotics arm or the robotic implement is doing something interesting or is in contact with the vegetations. But you have not really synchronizations between the mobile platform and the automated implement. And maybe what will be important in the future if we want to act directly on the vegetations or with respect to the Earth. Since we have deformable objects, maybe when we will try to move the implement or the arm, we will be short in terms of workspaces of the arm, and then we will have to move the mobile platform. And if we want to make further work, or if we want to make faster work, maybe we will have to drive the control of both an implement and a mobile platform with respect to the job to be done on the vegetation or on the Earth. But it's not so easy, since it's not because you have a mobile platform, a mobile platform, an articulated manipulator arm, you have a mobile manipulators, but you see that the connection is not so direct. So there is, because there is redundancy. When you want to move from one point to another, you can move the arm, or you can move the mobile platform, or you can move both. And so how to do the synchronizations, management of redundancy. We have a lot of work in the literature in this robotics problem, which is a typical robotics problem, which is partially solved in some environments when everything is okay without perturbation and so on, but it's not totally resolved when we are moving in natural environment or when we are considering that we are working with deformable objects. So one of the main topic is to do, I have a complete model of robots, not just an addition of a mobile platform and a mobile arm, but complete robotic systems. I modelize it, I add some constraints, and I can invert the equations, so the matrix, which is given by the model, and it's supposed to work. The fact is that in order to do that, we have to be sure of the system is well modelized. But in natural environments, we have a lot of perturbations, and we cannot be sure that the model is totally known. And moreover, the interaction matrix is variable. So what can be proposed is to use backstepping approaches. So we can try to develop several controllers who are acting in parallel. So for each kind of task, I want to take an object, I want to follow a trajectory, we can develop some different controllers. So if you want to reach an object, you can say to the arm, try to reach the object. You can say to the mobile platform, try to reach these positions. And both have the same objective, but they do not achieve this objective by the same way. So one possibility is to work step by step. So you tell the implement you have to grasp this object. If the arm can do it, it's perfect. If it can not do it, then you will meet some constraints. And if constraints appears, you will say, okay, stop the motions or reduce your motions and make the mobile platform move. And then if there is new constraints on the mobile platforms, you can say to the mobile platform, you can't move anymore, and it's the time for the arm to move. So we can make a competition of several control laws. So one control law, I won't go so deep in the detail. Don't be afraid. It's maybe the only equations you will see. A control with respect to the ARM, a control with respect to the mobile platform, and then having a weighting function which permits to optimize some of the constraints who can appear in the task. So one of the main constraints which appears when you try to interact with the vegetations, for instance, is the workspace of the arms. You know that a manipulator robot, your arm, if you doesn't move your feet, your arm has a limited workspace. I can go more than this. So when you will try to reach, when you will try to grasp an object, if it is within the workspace, everything is okay. But if you then go through the limit of the workspace, which depends on the elevation also, you will say, okay, I can't do anything more, so I will define a weighting function which will permit to switch or to have a ponderations, weighting, between the elementary control of the arm and the elementary control of the mobile manipulator. So we can do this we have applied that for this kind of operations, which is the PhenoFold project. So the idea is to make phenotyping, autonomous phenotyping of plants in all the field. So one elementary behavior is to make the convergence of the camera which is mounted on the end effector of the manipulators to take some pictures on the green box. So it's just an academic example because you don't move the plants while you are taking pictures, of course. But it's just to see that when I am moving the green box, so the arm starts to take pictures of it, so to have a relative position with respect to the green box. And if it doesn't succeed in having taking the pictures because you are close to the limit of the workspace, so the mobile platform here starts to move. So you can imagine that this degrees of freedom here is only can be a mobile robot, the trajectory of which can be chosen. And then we can make an iterative work. And on these pictures, you see that with the camera, we detect the feuille. Right. Sorry? Leaves. Sorry, thank you so much. Sorry again. Leaves. And as we have detecting leaves, we take pictures of leaves. When we have take pictures of leaves of plants, we go to the next plant, and we can see it by the camera. The arm tries to reach the leaves. It touches the limit of the workspace, and then the control of the trolley of this part, this part will take we'll take the power, and we will move. Sorry, we will move this part. Okay, and then this is just an example, and we can generalize this point of view and this backstepping approach to a mobile manipulator in order to follow a trajectory or to make posture manipulations. So we have here the coordination in between the robotic arms, which tries to follow its trajectory, and succeed in following its trajectory, while the second part of the control, which is the mobile beds, is able also to reach the trajectory. It works with skid steering robots, such as this one. It works, so for the moment it's theoretical. It works with two-wheel steering robots, so not only an Ackermann, but a double Ackermann robots for front and rear axle are activated. And then we can extend the backstepping approach to coordinate the position and orientation of the manipulator arm the position of the mobile robots with respect to the trajectory, and also the orientations, because we have two wheel steer on the robot, the orientation with respect to the trajectory we want to follow. And then we have a beautiful convergences, despite some perturbations, for the mobile base to the good position, the right orientations, and also for the manipulator to the good positions and the good orientations. So we are quite happy with that. And an interesting thing is that above the workspace limitations, you can add some other constraints, such as the occupancy grid, and to say, okay, I want for my manipulators to follow the trajectory. Up there, tuck, tuck. But the mobile platforms can do another trajectory, since we can have to avoid obstacles. But we can avoid obstacles while preserving the position and orientation of the mobile manipulators, and then we can manage the redundancy of the degrees of freedom in order to have the position of the arm, the position of the mobile robot. And then this backstepping approach, it's quite interesting to have an activated implement, but we can extend it also to consider that an activated implement can be a manipulator arm, but can also be a second robot. And then we can use this backstepping approach to control the position and orientation of a first robot. As soon as we get the relative positions, we can make the regulation of the second robot with respect to the first one. And then we have a kind of activated tool which relies on the first robots. So we have used that in the Adaptui project. And the idea of this project is to say, okay, I can have a fleet of robots. Depending on the task I have to do, I can use only one robot to do monitoring, field monitoring. But if I have to hold heavy loads, I can use two robots, or if I want to make complex applications, I can share a unique implement with several robots. The objective in terms of applications was to make spraying, so confined spraying. So with one spraying tool, one spraying tool on one robot, and the second spraying tool on the second robot, and recuperation bags, and something in order to cover trees, cover the vegetations, to avoid dissemination of chemical products in the atmosphere. Okay, so let's start with the first robot, as we are trying to have a regulation with respect to the vegetations. We use LiDAR, which is positioned up on the front of one robot. We detect some points, and so we group the points with respect to objects. So we consider that we have objects depending on the capability of the robot. That means the wheelbase and the width of the robot. And then we assume to have groups of points. As soon as we have groups of points, we look at if it's possible to go through between the hole. So for instance, here we cannot pass, so we consider that we will have only one trajectory. And then we define one trajectory on the left, one trajectory on the right. Or if we have only on the left, we are happy, only on the right, we are happy. If we have both, we are less happy because we have to make a choice or mean in between. But anyway, we can move by this way. We can make the control of the front steering angle, such as before, the control of rear steering angle, and we can control independently the relative positions with respect to these vegetations and the orientation and the positions. Okay. So as we have LiDAR, we can also use the LiDAR to detect if there is a hole in the vegetations and to adapt the spraying with respect to the presence of absence of vegetations, and we can cut some of the nodules depending on the presence of the vegetations. So we have a robot which is able to move, and now we will try to add a second one in order to make more complex tasks. To do that, we consider that the first robot moves and is oriented. We can define in the framework of the leader longitudinal distance, lateral distances, relative orientations, and then the objective of the control is to find steering angles and velocity, which permits to regulate the position and orientation of these robots with respect to these ones. But in order to do that, we need a local sensor which permits to have this position and orientations. We can't use GPS because we are close to the vegetations. We can't use LiDAR because possibly two robots are on both sides of vegetations, so we can see each other. We can't use also visions, so we have used radio frequency, and we have used an ultra-wideband sensor. So ultra-wideband sensor is a radio beacon which can be in a relationship with another beacons, and knowing the signals, we are able to define a distance between two beacons. And if we have a network of beacons, up. So here we have put beacons. Up. We know the position of each beacons. We have put two beacons on these Pumagri robots. So we know the distance in between the beacons on the robots, and then we can make localizations. We have tried outdoor because we would like to compare with the GPS, and we have almost a perfect correlation between GPS signals and UWB signals. So using this material, we can put 3 beacons on the leader robot, 3 beacons on the follower, making a backstepping approach to regulate the desired orientations, to regulate front steering angle, rear steering angle. We can do the same for the longitudinal point of view. We assume that we can decouple the longitudinal and lateral servoing. And then we are able to have a virtual link between robots. So the first robot is automatically controlled with respect to the vegetations with the first LiDAR. He can detect the vegetation with this one. He can adapt the noodle and the spraying. And the second one, which has not the sprayer yet, but it will come soon. So sorry. That's why I wouldn't like to present today, because we are not totally operational, but it's quite interesting too. And then at the end, the first robot can follow a trajectory using a GPS, or in this case, it is manually controlled with the remote controller there, and we can select to stay in the both sides, or we can say, okay, you can go behind me in order to make some operation. Okay. So we succeed in having some good results, especially in the lateral servoing. Here, during these phases, we ask to have 3 meters of lateral deviations between both robots to be at each part of the vegetations. And we are succeeding in staying at 3 meters plus or minus 10 centimeters. And it's about the same in steady state with respect to the longitudinal distance. We see that we have some deviation there and there because we arrived in stopping phases of the first one. So when you have fast variations of the first robot, you can't manage to have always good precision. We expect to compensate that using predictive approaches, such as you've seen with Mohamed. One thing which can help is also to have a communication in between robots. So for the moment, there is no communications, just they have the relative position and orientations. One interesting thing is if we can use the radio connection also to give some information from the leader to the follower, such as I will stop, my velocity, in fact, or the expected velocity if I am automatically controlled. I know that I will slow down. I know that I will accelerate. I know that I will turn right, turn left, and so on. And so using that, I can have better synchronizations. So what is interesting today is to say that Using robots in agriculture is not only autonomous navigations, it's also the control of one implement. We have to do the synchronization of automated implement and autonomous navigations. It's not so easy because there is redundancy and there is a lot of constraints we have to take into account. And to go further, we can use a second robot or several robots in order to have virtual tools and to enhance the implement capabilities of the robots and adapt also the number of robots, the resources we need with respect to the task to be done or the capability we need. For instance, one of the objectives in the future is to arrive to a mechanical connection between robots. So if you have to go in a high slope, instead of having a very large machine which is able to change the position of the gravity or the orientations, you can say, okay, instead of using one robot, I use two robots. The first one will help the second one will help the first one to stay within the slope without turning around. So we believe in that, and we consider that beyond the control of active implement, we will have to move to the control of cooperative robots to have an adaptable robotics system with respect to the agricultures. And that's all for me. Thank you. I can take one question, if you want, before switching to the other speaker. No question? Yes, Anthony?
In your concept of leader and follower, there is a major safety-related equipment that's the equipment able to give relative position from the follower to the leader. Is responsible, has a high responsibility. How safe is the technology provided in Orca or Vanilla?
I have not really an answer about the safety because it's not a material which is certified. There is no certification of that. The second problem is that you have in between the beacons, you are not allowed. It's better to avoid using steel or iron because radio cannot go through properly, and it's changed the accuracy. It's interesting for the vegetations because the radio signal is not affected by the vegetation, but it's affected by going through the iron or steel or something like that. But I don't know if today there is a UWB technology which has been certified and can be used. This point of view is interesting also because instead of having a first robot, you can have manually controlled machines and extending the automation of tools with respect to several robots. And it can be also a first step towards robotics in agriculture with respect to the acceptability of farmers.